Hello, I'm Cyprien Jourdain, and today I will talk about my project, which is the in-flight measurement of nanoparticle surface area and volume at the University of Cambridge in collaboration with combustion. We know that particle morphology is important in many fields, including climate modeling, industrial processes, battery technology, and aerosol instrumentation. The motivation for this work comes as there is currently no technique to measure surface area and volume in situ. So how can we recover these properties? The concept is to use a forward-backward approach, combining both modeling and experiments. The forward approach starts with a well-characterized bare aggregate, either using experiments or models. Then, we add a coating to this aggregate and measure its properties. The backward approach would be to measure the properties in the capillary condensation regime, and from these properties, recover the surface area and the volume of the bare nanoparticle. More fundamentally, there is a competitive condensation taking place on such quasi-fractal particles, and this is highly dependent on the relative humidity and the temperature. So the first requirement is then to characterize the limiting cases governing this competition, that is the capillary condensation regime for low saturated environment and the radial growth for highly supersaturated environment. Regarding the experimental setup, to be able to precisely control the particle enlargement, we first need to build a growth chamber. As in the CPC on the left, we first use water as the working fluid, but unlike in the CPC, we seek a controlled growth. With this first cylindrical chamber design on the right, we are able to impose the desired saturation history by using hot-wet walls, a cold-dry sample, and a cold-humidified sheath flow, both flowing from the left. Future work include the fabrication of the chamber, its integration and testing within a 3-stages instrumentation line consisting in the generation, processing, and measurement sections. Because heterogeneous condensation is an interplay between liquid redistribution and condensation, we have split this problem into two simpler ones. For liquid redistribution, the results based on CFD shows that the 4 monomers aggregate can be almost spherically encapsulated, while for a dimer, a pendular ring was formed. To study condensation, a stochastic approach was developed. The results show that the coating process significantly affects the dynamic of an aggregate. For both limiting cases of condensation, the mobility parameter ratio dropped during coating. For capillary condensation, there is a plateau before the rapid decline, whereas a linear dependency in the log-log space is observed for the radial growth. The growth factor by mass is increasing slowly for the first quarter of infraction and drastically afterwards. Future work includes the extension of CFD for buffer distribution and condensation, analytical modeling with condensation kinetics, and further simulations using molecular dynamics to model different wetting scenarios. Thank you for your attention.